I know. There we go. So I'm hoping you guys can all see that. Fabulous. Okay, thank you. Hi. As people said, my name's Emily. I'm actually in my first year doing my PhD here at Birmingham, working with Bill Chaplin. But I'm here today to talk about how TESS can contribute to the field of astroseismology. So specifically how we can use TESS data to bridge the gap between the main sequence and the red giant branch. So while I'm doing this, I'm going to introduce a pipeline that we've been developing in Birmingham to automate the detection of solar-like oscillations in large data sets. And as Mikkel said, that is in anticipation of the upcoming Plato mission. And then I'll also talk about a catalogue of oscillators that we detected in the short cadence data from TESS that sort of naturally fell out of work on that pipeline. And that's going to address the title of my talk today. So on that note, actually, I should explain what I mean by the gap between the main sequence and the red giant branch. So spoiler alert, it is related to the Hertzsprung gap, but not entirely. So when we talk about astroseismology to the community at large, we tend to focus on its application to two major fields, right? We either talk about how well it works in the context of galactic archaeology, or we talk about it in the context of exoplanetary research. And if you think about it, those two fields focus on two very different types of star in terms of evolutionary state. So in the exoplanet field, we're looking at stars in the main sequence, whereas in galactic archaeology, you're focusing on the more evolved red giant branch stars. So on the face of it, it looks like we're not paying terribly much attention to the stars in between or subgiants. So why is that? Well, of course, if you were to randomly pick a bunch of stars in the sky, you would detect fewer subgiants given that they're undergoing such a rapid phase in their evolution. But that's not the only problem that's sort of contributing to this lack of detections. We also need to consider that the majority of the solar type oscillators that we have observed currently, we observed using data from a single mission, the Kepler mission, which of course will naturally introduce whatever detection biases it had into those detections. So a quick reminder about the Kepler mission. We consider Kepler as sort of a gold standard for astroseismic data in terms of the solar type oscillator because of the long baseline. It stared at the same patch of the sky for about 4 years. And it looked at a lot of targets, over 150,000, I believe, in the nominal mission. Now, of the targets that Kepler did observe, it observed them in two main modes. Either the star was observed in long cadence, where the integration time is about half an hour. Now, in frequency space, that corresponds to a Nyquist limit of about 280 microhertz. Or the star was observed in short cadence, where the cadence is much shorter. It's about a minute, shifting the Nyquist all the way up to 8,000 microhertz. So for solar type oscillators and red giant branch stars, you're looking at frequencies below about 500 microhertz, meaning they're detectable both in long and short cadence, certainly in the more evolved cases. Whereas on the main sequence, you're looking at frequencies above a few thousand microhertz, meaning they are only really detectable in short cadence observations. So of course, that wouldn't be an issue if the total number of targets that was observed in both sets were the same, right? We wouldn't have a bias there, but that just wasn't the case. The majority of stars were observed in long cadence, and a much smaller set were observed in short cadence. I believe at any one time, only about 500 targets or so were prioritized for short cadence observations. So in terms of our detections, that means we end up with sort of a bimodal distribution in a way, right? We've got the more evolved stars that are observed in the long cadence observations, and then we've got a second set of stars observed in short cadence, which tend to be less evolved. We should also keep in mind the main aim of the Kepler mission was the detection of planets around stars like the Sun, which means those short cadence slots were prioritized for stars on the main sequence. So again, that leads to this sort of less evolved tendency in those detections. And you end up with the distribution that you can see on the seismic HR diagram here. So I don't know if you can see my mouse, but I'm pointing at it. So this is a seismic HR diagram. It's nu max on the y-axis rather than luminosity. And then, of course, effective temperature, and then I've included some evolutionary tracks there. So you can see the issue. We've got this massive density on the red giant branch, and then there's that sharp cutoff, which is induced by the long cadence Nyquist frequency. And then the density of detections really drops, and it only really starts to turn up again once you reach the main sequence. So to put this into context in terms of numbers, I believe the largest catalogue I've seen specifically of subgiant stars constructed using Kepler data was made by Lee et al. In a series of papers from 2019 to 2020, I believe. And there's only about 50 stars in that catalogue, which of course you can compare to the thousands of red giants we have and the hundreds of main sequence stars. So there's the issue, and that's the gap I want to talk about. I was a bit dramatic with gap. It's more of a drop in density, but gap sounds better. So how should we solve this, and why should we solve it, really? We know that seismology works really well in terms of red giants and with the main sequence stars, so is there any real point or merit in studying subgiants? Yes. Firstly, we need to consider the fact that stellar parameters that come out of seismology are often used as calibrators, for example, surface gravities. So we need to make sure we're not introducing any evolutionary state bias into whatever results come out of those calibrations. Secondly, we should consider the main aim, again, of Kepler and the upcoming TESS mission, which is the detection and characterization of exoplanets. We should consider the fact that the detection biases here sort of go in opposite directions on the HR diagram in a way. So as a star evolves, it gets larger and more luminous. That increases mode amplitudes, making detections from astroseismology a little bit easier. But on the other hand, as a star is getting larger, the depth of a transit given by a planet of a given size is going to decrease, right? Making detections of small planets around larger or more evolved stars more difficult. So hopefully subgiants should sort of walk the regime between the two. They're larger and more luminous than their main sequence counterparts, which will aid in astroseismic detection, but they're not so large as those red giant branch stars. Finally, we can come at this from an entirely selfish stellar physicist point of view and consider the unique opportunity to study mixed modes, which start to be exhibited in the spectra of subgiant stars. So I will mention in a minute a work that was done in 2021, and there's a good vibration seminar on this from the first semester that sort of goes more in depth on subgiants, but I'll just do a quick overview. As a star evolves off of the main sequence, its core is contracting and getting denser. That increases the Brunt-Weisseiler frequency in the central region, which increases frequencies of gravity modes, but the outer layers are still expanding, which is decreasing the frequencies of pressure modes, and at a certain point those two modes can couple, and you get what's known as a mixed mode. So it's a mode that behaves like a gravity mode in the core, but a P mode in the outer envelope. So now we've got something that's sensitive to conditions in the core. So if you can include these mixed modes in your modelling process, you end up with a better precision on age, because most of the rapid evolution is happening in the core. You can also use young main sequence stars to study the conditions in the core of that star while it was on the main sequence. So this is when I'm referring to the Good Vibration seminar. It's on work by Noll et al. In 2021, where they use a young main sequence star to constrain the convective overshoot, I believe, above the core. And finally, in 2020, Li et al. Noted a mass dependence between the large frequency spacing and the period spacing of dipole mixed modes in subgiant stars. So that allows you to have some constraint on the mass. So hopefully I've proved to you that subgiants are interesting and they're certainly useful stars to study. So how do we study them using astroseismology, given that they're in this rapid phase of evolution? So what we need, right, is a massive set of observations, or a very large set, a huge number of stars from which to select these types of star. And this is where TESS comes in handy, because TESS is surveying 80% of the sky. It gives us access to a huge number of targets to work with. Now, the observing strategy of TESS is fairly similar to what was happening in Kepler, in that the majority of stars are observed in long cadence, or sort of a long cadence. It's called a full frame image, with an integration time of 30 minutes. Again, that's giving you that Nyquist frequency of 280 microhertz, so it doesn't really help with the subgiants. And then there's a smaller set of stars observed in short cadence. Here the integration time is 2 minutes rather than a minute, so the Nyquist is down to 4,000 rather than 8,000, but that's still enough space for the subgiants. And then you've got something called fast cadence, or I've labelled it here super short cadence. There the integration time is 20 seconds. So that's a cadence that was introduced in the extended mission, so there's an extremely short list of stars that have been observed so far in 20-second cadence. So I'll focus on the 2 minutes here. So although fewer stars are observed in short and long cadence, of course, because TESS is looking at so many stars in total, that shorter set already constitutes in excess of 200,000 targets. So that's an excellent playground for us to look for oscillations in. Now, we do have our own challenges to address when it comes to TESS in comparison to Kepler, and the majority of these are related to the noise. So unlike the 4-year baseline of Kepler, the baselines on TESS are just much shorter. So to observe so much of the sky, TESS splits it into sectors and then observes each sector for about a month or 27 days or so at a time, which means the majority of stars are only observed in 1 or 2 sectors. There are a couple of regions near the poles where all the sectors overlap, and there you can get a year's worth of uninterrupted data. They're known as continuous viewing zones, and then double that in the extended mission, so 2 years, but of course that's just not the majority of targets. Also, the pixels on TESS are much larger than they were on Kepler, again adding to the noise. So all in all, I believe you have to observe a star that's about 5 magnitudes brighter in TESS to achieve the same noise level that you had in a Kepler target. So to mitigate these two factors, the stars that we observe with TESS are just much brighter. You can see the distribution in 2 mass K magnitude on the slide here. So in blue, that's all of the Kepler targets, and then in red, that's just the targets that have been observed by TESS in short cadence. So you can see at TESS, the density peaks at around 9th magnitude, whereas with Kepler it was around about 14. So that's that 5 magnitude difference that you're seeing. On a totally different note, we also have the issue, which is just becoming more of an issue as we move to full sky surveys, which is the total number of targets just being so vast. So 200,000 stars is excellent if you want to look for a very specific type of star, but it does mean without automated pipelines, you're searching through spectra of 200,000 targets, which is just not an attainable task. So we really do need to be automating the process. We need to be automating both the calculation of seismic properties like nu max and delta nu, but we also need to automate detection of solar type oscillators. So that brings me to the main aims of the work that I'm doing over the past year in Birmingham. So firstly, in Birmingham, we want to develop a pipeline that automatically detects oscillations. So as we said in the beginning, this is being designed with Plato in mind, but of course, TESS is still observing, so can be used on upcoming data releases from TESS. And then secondly, to build that catalogue of oscillators in that subgiant / low luminosity red giant branch regime, where the detections were sparser from Kepler. So I'm going to start, unsurprisingly, with the first aim here, and talk about the pipeline that we've been working on. So we've coined this pipeline ATROPOS, which stands in a maybe convoluted way for automated recovery of P-mode oscillations. And essentially, ATROPOS, we want it to take us all the way from detection through determining global seismic parameters to peakbagging where we can. So I'll focus firstly on the detection aspect. We function basically on 2 main modules. One is entitled power excess, which we sort of shorten to PE, and one is entitled frequency spacing or repeating pattern RP. So I'm trying to avoid using PE and RP as much as possible, but if it slips out, it's because I've been saying it so much, so that's what they mean. But those 2 modules are inspired by some of the most fundamental properties of the solar type oscillator in frequency space. So I've got a diagram here. It's a spectra of a star observed by Kepler, made by Chaplin et al. In 2014, but that highlights the 2 things that we're looking for here. So the first module, power excess, is looking for signatures of the power included in that Gaussian-like envelope that modulates the power of the modes. So we can look for signatures of that. And the second module, the frequency spacing module, is looking for signatures of the large frequency spacing, which is another unique identifier of the solar type oscillator. So let's get more in depth, and I'm going to talk about the power excess module first. So I've got a bit of a game of spot the difference here. I got 2 spectra, one of which is a solar type oscillator and one of which is just white noise. And I'd ask you to figure out which one is the solar type oscillator, and if you had any experience with the data, you would immediately say, oh, it's this one here on the left. So at first glance, the easiest way to tell the difference, right, is you've got this massive power excess present in the solar type oscillator that's not there in the white noise case. So that gives us some null hypothesis to test, right? We can ask if the power present in a spectrum is consistent with what we'd expect from white noise. Right? Is there any excess there that we can't explain with white noise? And we can use that to calculate a H0 probability. So we're just using here the normal chi-squared 2 degrees of freedom statistics. But I've got another case here. So again, one is a solar type and one is not. Hopefully we'd all say, again, we've got the same solar type and then this spectrum is something else. Although there is a power excess present there, it's got nothing like the characteristics you'd expect for the solar type, right? There's no Gaussian shape and the power is just appearing essentially in one bin. So that gives us a signal hypothesis to test. We can ask the question, is the power excess that we're seeing consistent with what we'd expect for the solar type oscillator, given everything we learned from Kepler? So that's our H1 hypothesis to test, and again, we can assign a probability to that. And then to determine whether we think we've detected oscillations, we basically can just calculate an odds ratio, right? Which one is more likely? So we need to do this in an automated fashion. And for an example, I've included a star observed by Kepler here. So you've got the spectrum, in grey that's unbinned, and in red that's binned data, and then at the bottom this is a merit function, which I will talk about now. So to automate this, we need to scan through in frequency space and ask these two questions at each bin in the spectrum. So we start at low frequency, we make the argument that the frequency that we're sitting at is equal to nu max, and there's an envelope there, sort of. And then we use that to calculate the width of the envelope that we would expect to be there if that was indeed nu max, using the scaling relation that we see on the slide here. So then we just sum the total power that we observe in that width, and we compare it to what we'd expect given the statistics of the spectrum just for white noise. So that's the H0, and that gives you a probability there. And now we need to calculate H1, but of course we need some prediction to compare to. So to do that, we again make this argument that this test frequency is nu max, and then we use the assumption that the envelope would follow a Gaussian shape and just use the Gaussian distribution, which you can see up there. So we have relations for everything in this apart from the height of the envelope. So we need some relation that gives us the predicted height of the envelope given the test frequency. So I've hidden the maths here. Essentially, it's a bunch of manipulation of scaling relations. It comes mostly from the maximum amplitude, but at the end of the day, you end up with the relation that you see on the slide here. So you've got the height of the envelope as a function of nu max, and then there is an effective temperature there, which we will need an independent measurement of. There's no way to avoid that. So we can substitute the test frequency for this nu max parameter and then calculate the HM, put it back into the Gaussian, and then just sum that power over the width of the envelope. So now we can compare the total observed to what we predict given these relations. So that gives us a H1 probability, and then we just do that for every frequency in the spectrum. And then you can calculate the merit function, which essentially is we just apply Bayes' theorem. So you can see the response here for this star. You've got this big lump in the merit where the envelope is appearing. So if you wanted to isolate solar types, you would just ask for any star where the merit function exceeds some threshold that you set. It also, of course, gives you some estimate of where the envelope is because it is a distribution in frequency. You can imagine, though, because this predicted height is decreasing with frequency, that at a certain point, if you go far enough in frequency, you reach the point where the total predicted power is fairly similar to what you get from noise, and then the merit just goes to 0.5. You can't tell the difference. These two situations look essentially the same. So to try and clean things up a bit and just avoid that, we wanted to introduce a prior, and we chose to take a prior on nu max. So essentially, we again are manipulating scaling relations here, but you end up with this relationship that you see where nu max is dependent only on the radius and the effective temperature. Of course, we already need the effective temperature for the predictions, so we take that as a given. And then for a radius, we can use a few measurements. So we take a magnitude, a parallax, and a bolometric correction to calculate a luminosity, and then combine that with an effective temperature for a radius. So by default, ATROPOS uses 2 mass K magnitude, but in principle, you can use what you like. So that gives you a guess on the nu max parameter, and then you can apply a prior. We select just a log normal prior, and it's fairly wide. I believe the width is 0.5 dex at the moment. Essentially, it's just to cut out those high frequency issues. So that takes you to the end of the power access module, and that's how it functions. But you can imagine some scenarios where a star might not pass whatever threshold you set, right? If that star has a power that is different from our predictions in some significant manner, and you set some threshold, it might peak just below that threshold, and you'd miss the target. So an example of a case where that could happen is we know that in some evolved stars, we see depressed dipoles, which decreases the total power, and that could cause an issue. So to try and avoid that, or to just introduce a complementary test that we can use to reduce false positives, we decided to introduce another module. This is the second module that I talked about in the beginning, and this module looks for signatures of the large frequency spacing. So I've got another spot the difference here. Again, you've got a solar type and just white noise. Now, if you look at the unbinned power in the background, it'd be pretty hard to isolate where the envelope is, or if indeed there is one. But then when you look at the bin power, the dead giveaway is that you see like this repeating pattern present there from the large frequency spacing. So that's the inspiration behind the test. Since we're looking for signatures of delta nu, it seemed like a given that we should use an autocorrelation function, which we commonly use to measure delta nu. So all of the following is it was set up based on the work that was done by Motter and Apishau in 2009 on using the autocorrelation as a function of lag. So you take the Fourier transform of the power spectral density, and then you end up with an autocorrelation as a function of lag. Of course, again, we want to do this in an automated fashion. So we start at low frequency again, make the assumption this test frequency is nu max, use that to calculate the width of the envelope, and then we calculate a cosine or a cosine squared filter, namely the Hanning filter, centered on that test frequency with a width given by the width we calculated, and apply that to the spectrum, and then take the inverse Fourier, and you end up with the autocorrelation as a function of lag based on that prediction. So then you can just do that for every frequency in the spectrum, and you set up a two-dimensional map like you can see here. So this is the results in the star that I showed you before. So on the y-axis, you've got the test frequency, which of course is our proxy for nu max. And then on the x-axis, you've got the lag, and that's the proxy for 1 over the large frequency spacing. So the color tells you the response from the autocorrelation function. Now we can whittle down parameter space because we know that there is a relation between delta nu and nu max, right? It goes as a power law. So we expect some sort of region to be more applicable to the solar type oscillator, and we apply those. You can see these red lines here just set up based on that power law. So to now calculate the distribution as a function of frequency, all we need to do is to collapse along the lag axis, and you end up with the collapsed ACF that you can see in the bottom panel here. So you've got this sort of variance going in the frequency. That's just caused by the Hanning filter. Of course, it had a width that was changing with frequency with nu max. And then you've got this big lump, which is the response from the envelope. So we can compare this to what we'd expect for just the noise statistics and calculate another merit function based on that. And you can see the response here in this panel. So again, there's this massive lump where the envelope is present. You can take a threshold and isolate your oscillators by that, and it also tells you sort of where those are. So I should say in the beginning we also said that we wanted ATROPOS to measure the global seismic properties, and of course we've got the mechanism for measurement already set up for us. Since we know we can use autocorrelation functions to measure delta nu and nu max. We get to nu max just by the collapsed autocorrelation that you can see here. And then we do a similar thing. You can collapse along the frequency axis and you get a distribution in delta nu, which you can use to measure delta nu. So that's how we get the global seismic parameters from this autocorrelation. And that is essentially the whole throughput of ATROPOS as it is right now. But I've left quite a lot of things out, right? I haven't told you anything about the performance. I've said we can take thresholds on the merit functions on the power excess and the repeating pattern tests, but I haven't told you what sort of threshold you should be looking at. And then I said, well, you could use two modules to pick up oscillators that don't match predictions, or you could use them to whittle down false positives, but I didn't say which is sort of the right way to go. So to calculate all of these things, we need a training set of oscillators, right? We need a set of stars which we know are solar type oscillators, and we need a set of stars where we don't believe we can detect oscillations. So to find that set, we decided to kill two birds with one stone in a certain sense, since we knew we also wanted to build up a catalogue from TESS, and decided to look at TESS observations. Now that sort of introduced a circular issue, right? I mean, there's 200,000 targets to look at, and we're developing pipelines to avoid that problem. But fortunately for us, we had access to something called the Asteroseismic target list. So that was constructed by Matthew Schofield in 2019 during a PhD. Essentially, it was pre-allocation of TESS observations. It was the stars that we would like to observe in short cadence for astroseismic purposes. So that's stars where nu max values from classical parameters predict nu max in excess of the long cadence cutoff with a bit of wiggle room. It's 240 microhertz rather than 280. And then they did a similar calculation to what we do in RH1, and they calculated the predicted amplitudes and then compared them to the noise, and then retained only stars where there was a 5% probability that you'd be able to detect those oscillations above that noise. So all in all, the list in its first form was 25,000 targets long. We managed to access data for 11,000 of those stars, and then we just performed a manual search using spectra, light curves, and HR positions. So essentially, we categorized stars into one of three groups. Either they were clearly solar type oscillators, they were probably solar type oscillators, but we couldn't really be sure, or there was no clear evidence of solar type oscillation in that data. So this brings up an important point. I'm not saying these stars are not solar type oscillators. I'm saying we can't make a detection in the data that we have. So essentially, you just wouldn't want them popping out of your pipeline. So of the first set of the stars where we have clear oscillations, that set is about 600 or so targets long, about 678. And then we just randomly chose 400 to use as a training set. So of the non-detects that we wanted to use to calculate false positive rates, we needed to make sure those two sets were comparable. So on average, the non-detects are dimmer. That's not something you can get around. If they were brighter, we'd expect that we detect oscillations, so we can't really avoid that. We also noticed on average they were slightly hotter than the stars where oscillations were present. And that's because in the initial construction of the astroseismic target list, there was a non-negligible number of stars that were included that were slightly hotter than we expect, because the authors wanted to study the transition between classical pulsators and solar type oscillators, so the so-called hybrid stars. So to avoid those stars, all we did was weight our random choice in the non-detect by the effective temperature distribution of the detections. So once you've done that, you end up with these two catalogues, or these two sets that you see on the seismic HR diagram here. So that sort of gold colour is the non-detections, and the turquoise colour is the detections. So they seem fairly compatible. Then all we did is run ATROPOS on these stars, and we vary the thresholds that we take on the tests. We also asked the question whether we should ask for responses in both modules or just a single module. And then we constructed the false positive, true positive curve that you can see on the slide here. So on the y-axis, that's your true positive, and then on the x-axis, that's your false positive. So each individual line on this plot corresponds to a specific cut on the power excess module, or the power excess merit. And then each scatter point consists of a cut on the repeating pattern. So immediately what you'll notice is there's not too much scatter between the lines, that there's not too much spread. Which means you can essentially take a fairly arbitrary cut on the power excess merit and then just make up with it by tweaking the cut you take on the repeating pattern. Now the dotted lines on this half correspond to places where we asked for responses in both modules, whereas the filled lines correspond to places where we asked for responses on a single module. So that's a so-called AND or an OR statement essentially. And I've just drawn this dotted line to delimitate the two. So of course, as you'd expect, if you ask for responses in both modules, you get the fewest false positives, but you also get the fewest true positives. Whereas if you ask for a response in a single module, you get the most true positives, but you also increase the false positive rate, which is what you'd expect. So whatever you select depends on what you want, right? If you're not so worried about looking through false positives, you just want as many solar type oscillators as you can get. If you take a cut on the power excess and the repeating pattern of 0.8, you end up with a true positive rate in the region of 90% and a false positive of about 14%. On the other hand, if you're not so concerned, or if you are concerned about false positives, you want a clean set of stars, you can ask for an AND condition. Again, the same 0.8 will give you a true positive of 70% and a false positive rate of about 3%. So that is the performance in TESS. And that actually brings me all the way through what I wanted to say about that half of the pipeline. And now I can talk about that catalogue of stars that fell out of that work. So the stars that we drew training sets from. Of course, we can use ATROPOS to determine the global seismic properties, nu max and delta nu for those stars. But before I comment on any of that, I should probably bring up how accurate we believe those parameters are. So of course, it was pretty difficult to come up with a list of stars with reported values of nu max and delta nu from the literature that exist within that set, because in the majority of cases, these are new detections. But we have a list of about 10 stars here, I believe. If anyone has any more examples, I'd be happy to see them. And these stars are observed across different short, long, and fast cadences. And then there's another star, Beta Hyades, in there, which was included where oscillations so far have just been detected in Doppler velocity air. That was just sort of an interesting start to look at. So we can run ATROPOS on all of these targets and calculate fractional residuals, and you end up with the distribution you can see here. So you've got the fractional residual on one axis, and then whatever we're measuring. So delta nu on the left and nu max on the right. So the first thing you notice is there's this star where there's a massive residual, and that's because we don't make a detection. The authors that reported the detection from TESS data said that they required a manual reduction on that star, so we weren't so surprised that nothing came out of that. We also used the 20-second data on the stars that were detected in 20 seconds, so I've just highlighted that they're these high Newmax targets. So I can remove that manual reduction required star just to make things clearer, and you can see the distributions here. So in delta nu, you expect a fractional residual of a few percent. We weren't so surprised by that. Of course, we're using fairly short data sets, which will impact the quality of an autocorrelation function. And then in Newmax, the scatter is slightly larger. It's on the order of 7% or so, I believe. But again, it's not something that was terribly surprising to us, since the actual formal definition for Newmax tends to vary slightly between authors. So that gives you a feel for sort of the way that ATROPOS measures delta nu and Newmax. And now I can measure Newmax and overlay these stars on that seismic HR diagram to see if we've addressed that issue of measuring stars on the subgiant or the sparsely populated regime. And here it is. So again, we've got the Kepler detections on the left, and then I've just overlaid the Newmax values that came out of ATROPOS for the catalogue stars on the right here. So as you can see, they fill out that region very nicely. They sit right below the cutoff for the long cadence observations from Kepler, and then they start to populate the subgiant regime, and then they're moving towards the main sequence. And of course, the majority are more evolved rather than a bunch on the main sequence, and that's just because the more evolved they are, the larger, more luminous, and we are dealing with short data sets, so they're easier to detect there. Now you're going to notice the spread on temperature here. So the temperatures that I'm plotting come directly from the Asteroseismic target list, and there they wanted a homogeneous set of effective temperatures, so they essentially just use a fit to photometry, which again could introduce some errors. Some of these strong outliers are stars where they're extremely metal poor, which means that fit is probably not so great. But either way, that shows that we've achieved that aim, and we can. Although we can't comment on all of the Newmax delta nu in terms of comparison to other studies for all of these stars, we can make a comment on how accurate we believe they are based on the power law between delta nu and Newmax, which we know exists. So this is log 10 delta nu on one axis and then log of the Newmax on the other. So with the power law, right, we're expecting just a straight line in the middle. So I've also coloured the plot points by how many flags they flag up in ATROPOS. So the lighter is stars where there was just one response, and then the darker is where both modules flagged. So you can see, as you'd expect, stars where both modules flag seem to follow that relation the tightest. Of course, these are the clearest detections of solar type oscillators, so that's not surprising. And then you can see there's a larger scatter on the stars where they are only observed in one module. They only flag a response in one module, and in a lot of cases the uncertainties are larger. One thing that your eye will probably be grabbed by is this huge uncertainty on this star here, which you think, oh, what's that? Well, here's a star where there's no significant response in the repeating pattern, so essentially the delta nu and Newmax that come out of the autocorrelation are just a representation of the prior. So we actually haven't really learned anything there. And then you've got these other outliers that you can see up here, and these are places where there was some spike at low frequency that sort of threw off the repeating pattern that we are currently looking into what actually caused that. And then you can see some triangles here, and these are just stars that were probably misclassifications in our original search. Of course, we did it by eye, so it wasn't entirely perfect. Okay, so that is the catalogue as it stands. We have these 600 or so stars. It's actually up to 730, I believe, at the moment, with Newmax and delta nu. And what's coming next? What do we want to do next? Well, as I said, we want to take stars all the way from detection to peak bagging. So we do want to locate positions of individual modes. Now that will help us improve our global parameters. So delta nu and Newmax improve when we peak bag. And then we can also make those frequencies available for modelling. Okay, but you might say, but how many stars do you actually expect to be able to peak bag, given the majority of stars observed by TESS are only observed for a few sectors? So you can see of the ATL, the distribution in length here. And yes, the majority of them are short data sets. Well, actually a substantial number. We've been going through the spectra just by eye and inspecting, and I've got two examples here. So on the left, this is a spectrum that was observed for just one sector, actually slightly less. I think some of the cadences were thrown out. And then on the right, you've got a star that was observed for about a year. So of course the resolution is better, but what's really lovely is that you can clearly make out the positions of individual modes even with this short data set. So that's really exciting. And I haven't just picked out my favorite stars, and to prove that to you, here are the first 30 in the catalogue. There's just been spectra for them. In red there, that's the star on the previous slide, and the next 30, and the next 30. So you can make out the positions of lots of individual modes in those spectra. And now, how are we going to do this peak bagging? Since we want ATROPOS to be pretty much fully automated, well, this is where another pipeline that has been developed in Birmingham comes in handy, called PBJam. It's been worked on currently by Nielsen et al. And essentially, at some point, we want to merge these two. So PBJam will automatically recover 0 and 2 mode pairs, or L equals 0 and 2 mode frequencies. And the way it does that is it takes some input parameters. So importantly, it takes estimates of nu max and delta nu, which is helpful because we have them from ATROPOS. It uses those to set up an initial guess on where the frequency should be based on the asymptotic relation and a massive prior that's built out of Kepler observations. It then peak bags stars using that asymptotic relation, but then it sort of releases the strong constraints of that and allows frequencies to vary slightly and does pair by pair peak bagging. And it then returns frequencies and other oscillation mode parameters. So you might think, oh, you've mentioned a prior here based on Kepler, and we are sampling in a regime where Kepler sort of struggled. There it is. Yes, that is true. We are in a sort of sparse region in prior space. So to overcome this, we're going to have to be slightly more careful. What we're going to do is start at the most evolved stars in our catalogue, where the prior is densest, peak bag, and then fold them back into the prior so that we can slowly build up the prior as we move towards the main sequence. So that will allow us to peak bag these stars, and it will also improve the prior that is currently included in PBJam, which will of course be helpful for upcoming missions. So to prove to you that this is a sensible idea, I've got some examples of results on stars in the catalogue. So you can see their positions on the seismic HR diagram in these little shapes here. So now we're looking at the red triangle. I won't say the full names because TIC numbers are very long, but you can see the star is oscillating around a frequency of about 330 microhertz, and PBJam does a pretty good job of returning L equals 0 and 2 frequencies. You can see them very clearly here. We can move to a sparser region in parameter space and look at the blue star. This is another star where we're oscillating at frequencies about 500 or so microhertz. And again, you can see that PBJam does a fairly good job at returning frequencies. And then finally, we can go to one of the least evolved stars in the set. This is actually Mu-Her, which has been studied before in Doppler observations. And you can see a whole host of modes, and PBJam does a good job of returning frequencies for those, even though it's in one of the sparser regions in parameter space. So that actually brings me to my conclusions. We've discussed the pipeline that we're working on at ATROPOS, and we've talked about the catalogue of stars that fell out of that catalogue, and then we've discussed where we're going next with those stars in terms of peak bagging and the pipeline in terms of combining it with PBJam. So TESS has given us the opportunity to massively expand the number of subgiant solar type oscillators we can study, which is an exciting playground for stellar physics and also to include in calibration and exoplanetary studies. We know that pipelines like ATROPOS, there's another pipeline called the Quick Look pipeline, I believe, which takes images and uses machine learning. These will significantly reduce the amount of manual vetting required. But given the extent of future surveys, even if you have a false positive rate of a few percent, you're still going to end up with thousands of spectra, which could be false positives. So manual vetting is likely not completely defeated yet. So in terms of the future and where we're going, of course, we want to return those frequencies, as I spoke about. We are also waiting on data from TASOC, which are asteroseismic ready light curves. So all of the work that I've done and spoken about today uses Spock light curves. So we do expect that some more solar types will pop out of the TASOC light curves, and then that catalogue will be bolstered there. And that's pretty much all I wanted to say today. So that's where I'll end my talk.
Excellent. Thank you very much, Emily, for this this great talk. So if people have questions, they can raise their hand, and then I will see if I can locate you here. So first off, we have Dennis Stello with a question. Please, Dennis.
Thank you. I'll just lower my hand. Thanks, Emily, for a great talk. You said you were looking for literature values of delta nu and nu max of bright stars. Mm-hmm. And I was wondering whether you had looked at the paper by myself, Bill, and some others back in 2009, where we have a list of stars going from main sequence to giants. There might be an overlap for your subgiant set, if you haven't already checked that.
These are Kepler observations, right?
No, so this is before Kepler. So they are just bright stars all over the sky, measured from ground.
Okay, I haven't looked at that yet, but that's something that I'd like to have a look at. So thank you for bringing that to me.
Okay, any more questions? Otherwise, I can ask a quick one. Given that you have used the ATL to test your pipeline, can you say something about the ATL in terms of is it too pessimistic or too optimistic, and how does the predictions made before the test mission actually correspond to the findings that you can make now?
Yeah, sure. So I didn't want to make too strong of a comment because, of course, we are using SPOC rather than Asteroseismic ready light curves. But there are certain things we can say. So the ATL essentially predicts a few thousand, I believe, detections. And of course, you'll say, well, you've only got 700 or so. But we do only have access to about half the targets, right? It's 25,000 long, and we only have 11,000. So there, it's actually fairly similar, especially given the fact that we're not using Asteroseismic ready light curves. But once TASOC comes available, we would like to go into a greater detail on that.
Okay, good. Yes. So next up, we have Tim Bedding.
Thank you, Emily, for a wonderfully clear talk. Oh, it's fantastic. So you didn't talk about background correction at all. Yeah. Did you do that, for example, in measuring nu max, and did you also measure amplitudes?
No, so we just use, in terms of background correction of the spectra itself, is this what we're mentioning? Yeah, so we use a moving median filter to remove backgrounds, and then we go from that, which of course isn't perfect. We could model it and do things like that, but this is sort of a quick look, so we haven't done that yet, if that answers your question.
Okay, see if there are any more questions. Otherwise, I can ask what are your expectations to, of course, this brings the arrow back on me on the TESS results, but in terms of using the 10-minute cadence data for full-frame images, that should increase the Nyquist to 800 something, I believe. So what are your expectations in terms of findings of low luminosity giants from your pipeline there?
Yeah, so far, I'm not sure how many extra. Well, certainly it's going to be all of the full frame targets, right, in 10 minutes. So certainly more will pop out. But the ATL essentially since we got 11,000, I guess the extra targets there can come from the full frame images. So maybe we double what we have.
Yeah, it might be worth looking into updating the ATL in terms of predicting for the 10-minute cadence and looking at those. Yeah. Then we have Paul Beck with a question.
Hi, Emily, this is Paul. A very nice talk. I was wondering how you deal with contamination, because TESS has the problem of big pixels. How do you deal with that? And how will this be a factor for Plato?
So I'm not sure about Plato. I think you'd have to ask committee members for that. But contamination is an issue. We know that there are big pixels on TESS, which we do believe is contributing to the fact we don't make the full thousands of detections that the ATL predicted there. Yeah, so it's just an issue that we have to come to terms with.
Okay.
So this will, but does this go somehow in the false alarm possibility, or will it be a long-term plan?
So some of those false positives are caused by background binaries in the large pixel that do throw off the pipeline. So we actually ran this through all of the short cadence targets and then measured Umax and made a comparison to prior to see how many stars where we detect oscillations on another star. It's not actually that many targets in the grand scheme of things, but it does introduce false positives. That's unavoidable.
Okay, thank you.
No worries.
Then I might ask another question. Have you considered making, now that we're talking Plato, and there's this Plato simulator that can simulate solar-like oscillators, including as much of the known knowns in terms of things that can affect the light curve. So have you considered doing a simulation study in terms of the usability for Plato?
Yeah, so we have run on simulations for Plato, I believe, and we did Kepler as well. Essentially, we ended up with very, very high false positive rates because we were comparing envelopes that were constructed using the same scaling relations that we take our H1 posteriors from. But I don't believe we've tested it in the sense of measuring nu max and delta nu, so that could be a shout.
Okay, it doesn't seem like there are any more questions. So if that is the case, then let's thank Emily again for a great talk. And I don't know, Rita, if you want to say a few words.
Yes, thank you very much, Emily, for giving this first seminar of the second season. I wanted just to highlight that so we have another, of course, in 2 weeks, another seminar that will be given by Guillaume Dréau from Paris Observatory. And then 2 weeks later, that will be the Plato conference. So we will not hold a seminar. And the next one will be on the 20th of October with Simon Bersens from Leuven. So thank you very, very much for staying with us and for continuing this adventure with the Good Vibration seminars. Thank you very much, Emily, and see you in 2 weeks for most of you.
Thank you for having me.
Thank you.